Okay, today we'll jump into section 2.2 in your textbook, which is on logically equivalent statements. So the last thing that we did on Friday was we said, okay, so if you have the conditional statement, if P then Q, then you can write down, at least 3 related conditional statements. And these 3 in particular have special names. And so if our original statement is if P then Q, then the converse is the statement if Q then P. The inverse is the statement if not P then not Q. And the contrapositive is the statement if not Q then not P. And we said that these statements don't all mean the same thing, right? Because if we let P be the statement, you get every question correct. And Q be the statement, you pass the class. Then presumably if P then Q is a true statement, but if Q then P is a false statement. So these two are not, a statement and its converse are different. Okay, so if we really want to get gritty with examining these statements, one way to do it is to just write down the full truth table. And then we can see, for example, that a statement and its converse are not logically equivalent because they'll have different columns in the truth table. So it's good practice doing a truth table anyway. So we have 2 statements, P and Q. We're also going to need not P and not Q, so might as well include those. And then we'll look at the conditional, its converse, its inverse, and its contrapositive. And this will be our truth table. And so I need 4 rows. This. And just recall that we said that what you do is you write down all the possibilities by sort of alternating with half the period. Okay, so now by the way, you should do this on your own. You shouldn't just trust me to do it. But I'll show you what the answer should be. So not P that has the opposite truth values as P. Not Q has the opposite truth values as Q. If P then Q is only false if P is true and Q is false. So that's here. Otherwise it's true. If Q then P is only false if Q is true and P is false. So it's only false here. Okay, so you can see that these 2 columns are not the same. So this says that a statement is not logically equivalent to its contrapositive, the conditional statement. Sorry, to its converse, Right, so you can even see why maybe in the second row, which is probably the situation that most of you will be in. Sorry, the third row, this is a situation that most of you will be in this class, where you're not going to get every question correct, but you will pass the class. And you see that those 2 are, the conditional and its converse have different truth values there. If not P, then not Q is false only if not P is true and not Q is false. And if not Q, then not P, the contrapositive is true. Sorry, it's false only if not Q is true and not P is false, which is here. Okay, so what do you notice here? What you notice here is that this column and this column are the same, and the 2 middle columns are also the same. In other words, a statement is logically equivalent to its contrapositive. Also, the converse and inverse are logically equivalent, but that's because the inverse is the contrapositive of the converse. And so its conditional statement is logically equivalent to its contrapositive. Okay, and there are many, 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 many times in this course and in other math courses where instead of proving a statement, you prove its contrapositive. So this is like maybe the first genuinely useful technique that you should commit to memory. Right? Let me try to come up with an example on the fly, something that's let's say we want to prove something like if something happens, then n is prime, right? So if box, then n is prime. Okay, and maybe something, I don't know, something goes in the box here. 2 to the n minus 1 is prime, then n is prime. Imagine this is something you're trying to prove, right? Of course, this is a little bit artificial because we actually started with the contrapositive statement back in lecture 1. But the point is that sometimes when you take the contrapositive, even though it's a logically equivalent statement, for some reason, you get something that's easier to prove, right? So like I said, this is a little bit contrived, but here, if n is not prime, then 2 to the n minus 1 is not prime. So if you were asked to prove this first one, it would be enough to prove the second one because they're logically equivalent. Why is the second one a nicer statement to prove? Well, because in the second statement, what you get to assume is you get to assume that n is not prime, which gives you something very concrete to start out with, right? If you start by assuming n is not prime, then you get to write n as a times b. And so you have like a concrete starting point. I know how to factor n, I can do something with this. Then I can sort of like plug it into here, right? On the other hand, it's not that clear what to do with this, with the statement 2 to the n minus 1 is prime, right? So if you try to prove the first one, then you're starting with 2 to the n minus 1 is prime. And there's sort of nothing concrete you can say. What that means is that it's not possible to factor 2 to the n minus 1. So you're not starting with a concrete thing that you can work with. And so because of that, to me, it seems very clear that the second statement is easier to prove because you get to work with more concrete things at the beginning. So a very common technique for the rest of your lives is if you're trying to prove a conditional statement, sometimes the contrapositive will lend itself more easily to proving. Okay. So many proofs will start with something like, we wish to prove if P then Q, it suffices to prove the contrapositive. So suppose not Q, and then eventually you conclude not P. Okay. Let's now make two important definitions. So the first is a tautology. So a tautology is a statement that is always true. Okay, so I think the easiest way to demonstrate a tautology is to give an example. Okay, so the statement, if P then Q or P. Okay, so this is some statement. And in order to understand it, the nice way to do that would be to write it down its truth table. Right? So probably as an intermediate step, I want to write down if P then Q, and then I can do the whole statement like this. Again, 4 rows. True, true, false, false. True, false, true, false. We've now done the truth table for the conditional statement like 100 times. So it's false here and true otherwise. And then this last statement, if P then Q or P, will be true as long as one of the first and the third column are true. But that's true all the time. So regardless of what P and Q are, the statement, if P then Q or P, is always true. So this statement is a tautology. Okay, some other tautologies, which are maybe sort of easier to understand why they're tautologies, is statement P or not P. This is a very classic tautology, right? Because every statement is either true or false. For every statement, either it's true or its negation is true. And therefore P or not P is always true because exactly one of these will be true and one of them will be false. Okay, another example, P if and only if P, n is prime if and only if n is prime, right? Or for the first one, n is prime or n is not prime. Those are both always true statements, regardless of what the statement is. If P, then P. P implies P. And then maybe harder to see, so maybe you should do a truth table for this, is if P then Q or if Q then P. This, it turns out, is always true. Okay, so that's what a tautology is. The sort of flip side of that is what's called a contradiction. Since I have unlimited paper here, start a new page. So a contradiction is a statement that is always false. Okay, so let me give you an example that maybe we need to, again, do a truth table for. It's a statement P and Q and not if P then Q. Yeah, and this is one where it's maybe not so easy to see when this will be true and when this will be false, because it's sort of a complex statement. It's built up out of several simpler statements. And so what column should we have in this truth table? We should of course have P and Q. We should have P and Q. We'll need that. We should have if P then Q. We should have the negation of if P then Q. And then we should have the conjunction of if P of P and Q and if not, not if P then Q. Okay, so you should do this, but I'll just do it for you. P and Q, that's true if P and Q are both true and false otherwise. If P then Q is only false if P is true and Q is false. The negation of if P then Q is just the opposite of the previous column. And now this last column will be true if this column is true and this column is true. But that never happens. So this statement is always false, regardless of what P and Q are. So this statement is a contradiction. So that's just what we call a statement that's always false. Other contradictions include, maybe the most classical example is P and not P. Right? It's never possible for the statement to be true because it's never possible that a statement and its negation are both true. If a statement is true, its negation is false. So you can never have P and not P. And another example of a contradiction is P if and only if not P. Okay. So let me now ask a sort of only tangentially related question, but I think it's an interesting question anyway. Let's call this question. And it will be related. It just doesn't seem that related at first. And here's a question. Do we actually need all of the logical operators and or not if then, if and only if? Or can we get away with fewer of them? Perhaps a related question is, are there any logical operators that we don't have yet? Right? In other words, is there any column that I can't get in a truth table by using only these logical operators? So related. Do we have all of the ones we need? Okay, so you should think about this. if this were a live class, I would ask and I would wait for somebody to respond to me. But one thing that's maybe not so difficult to see is that P if and only if Q, so to say that P happens if and only if Q happens, is logically equivalent to if P then Q and if Q then P. And written out like this, it's maybe not that familiar, but you're used to using this kind of logic all the time in your life, right? So let's say I want to prove to you that if n is even, then n squared, sorry, n is even if and only if n squared is even, if n is a positive integer, say, then I could prove it to you by proving, well, if n is even, then n squared is even, and if n squared is even, then n is even, and that should convince you that n is even if and only if n squared is even, right? So maybe that's the thing to think about. N is even if and only if n squared is even. Say this one is if n is even, then n squared is even. Say this one is if n squared is even, then n is even. Maybe I should have done this in a different color. But it's clear, right, that if I prove to you that this was true and this was true, you would agree to me that this one is true. So in other words, I don't need if and only if. I don't need the biconditional. If I just had the other four, then I could express the biconditional in terms of just and if then. So I don't need the biconditional. I don't need if and only if. On the other hand, we use statements like if and only if so often that it's useful to have this logical operator to express this longer one, just because it'll it's a more compact notation. Okay, also, so here let's first of all put the statement if P then Q. We said many times that's false if and only if P is true and Q is false. In other words, so let's think about this. This is false if P is true and Q is false. Which means that it's true if P is false or Q is true. You might have to think about that for a second, but if P is false, then that conditional is true. And if Q is true, then that conditional is true. And the only time that it's true is if P is true and Q is false, which is exactly what you're excluding in the second line. So, I mean, or you could see this by a truth table, right? Maybe I should add that on the side. So if the second column is true or the first column is false, then the third column is true. In other words, this statement is logically equivalent to not P or Q. Okay, by the way, something I haven't mentioned is that negation binds the strongest, right? So if you want to be very unambiguous, you might write this as not P or Q. But if you want to express the negation of P or Q, you'd have to write this one. So because negation binds the strongest, these two are the same. But if you want to be very careful, it doesn't hurt to include more parentheses. So negation binds the strongest. I think all the rest of them bind equally strongly to one another. So you would need to use parentheses to to distinguish. So I mean, if you wrote something like, this is totally an aside, but I guess I never mentioned it. If you wrote something like P and Q then R, this is ambiguous because these three, sorry, these two logical operators are on the same footing, and this statement and this statement are not logically equivalent. So it does matter. Are they definitely not logically equivalent? Yeah, they're definitely not logically equivalent because if P is false, then the first one is true, but the second one is false. Okay, so these, so you would need to specify which one you meant. Here, it seems like I would need to do this, but negation binds stronger. Okay. So all that to say, this first example showed that I don't need if and only if, but this second example shows that I don't need the conditional either. So we can get away with just and, or, and not. Right, so if you've taken any computer science courses, this is because these three logical operators form a universal gate set. In fact, we don't even need all of these three. It turns out that we can get and from or not. Right, so actually, we don't need and either. That means that I need to somehow figure out how to write down a statement that's logically equivalent to P and Q using only nots and ors. So this is a good exercise. I think you should try to do it. So maybe I can tell you to pause the video and try to figure out for the next, I don't know, 5 minutes, how you could write P and Q, or a statement that's logically equivalent to P and Q, using only nots and ors. Okay, so thanks for restarting the video after you paused it. So I want to use just nots and ors. So from here, I probably don't want to jump straight to P or Q because P or Q we know is not logically equivalent to and P and Q, and negating it won't fix things either. So let's try by first negating P and Q and seeing how we could try to get P and Q. I guess I'll need a long one eventually. So true, true, false, false, true, false, true, false, 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 true, true, false, true, false, true. Okay, now I guess we just have to play around with this a little bit. We're trying to get something that's the column that I eventually want is a column that will look like this: true, false, false, false. And I want to get there by just using nots and ors. So let's see if let's just try something. Let's try oring P and, sorry, not P and not Q. In mathematics, oftentimes what you do is you just try something. So if we or this, we'll get false, true, true, true. Right? So that's something. At least this one, I mean, I guess, yeah, so this one has 3 trues and a false. Oh, we're actually already there, basically, right? Because this column is now the negation of the last column. So I can just negate this whole thing. So we tried something and it happened to work. Or it happened to be almost what we wanted. So what does this say? This says that not P or not Q is logical equivalent to P and Q. Which means that we actually don't need and either if we were going for parsimony, right? If we want to get away with as few logical operators as possible, it turns out that we don't need and because we can get it out of or not. Again, of course, since P and Q is a logical operator that we want to use super frequently, it's much nicer to have its own symbol for and its own sort of space in our head, rather than always wanting to think about not P or not Q. Of course, this kind of makes sense, right? Why should this sort of make some intuitive sense? Because when is this thing false? That statement on the right is false exactly if P is false or true is false. Sorry, P is false or Q is false. So this side is saying it's not the case that P is false or Q is false, which is the same thing as saying that P and Q is true. Okay, so if you think hard about this logical equivalence, I think you can even intuitively digest it. Okay, one thing I guess that I haven't discussed is if you have just not and or. So now we're down to, so we only need not and or. One thing I should have said is if you start with all five, then it's possible to get every possible column for P. If you have two statements P and Q, you can get every possible column just using ands, ors, nots, conditionals, and biconditionals, which means that you can get every possible column using only nots and ors as well. Okay, it turns out that actually, this is again just an aside, we actually don't even need both of these. So actually can get away with a single logical operator. Of course, you can't get away with just or just not, but you can look up NAND, which I think is sometimes written like this, and NOR, which is sometimes written like this. It turns out that using just NAND or NOR and parentheses, you can get every other logical operator. But the five that we discussed on the first day, we use so often that we want, it's nice to have all five if you want to express some sort of logical thought. Okay, but this last thing that we observed is kind of a nice observation in its own right. And let me actually just rewrite it slightly differently, which is let me negate both sides. So if I negate both sides of this, what you'll get? You'll get not P or not Q, because if you negate something twice, you get back to the original statement. And this is equivalent to not P and Q. And this tells you how to negate an and statement. If you want to negate an and statement, it's the or of the negations. And so this is a useful thing, and this is called one of De Morgan's laws. So De Morgan's laws. And it's just as simple as this. The negation of P and Q is logically equivalent to the disjunction of not P and not Q. And similarly, the negation of P or Q is logically equivalent to the conjunction of not P and not Q. So here's how you negate an and statement, and here's how you negate an or statement. Okay, and again, this is something that you can sort of intuitively grasp, but maybe in order to do this, the best thing to do is to look at an example. Okay, by the way, you can prove this by just using a truth table. Maybe I'll make this an exercise on your homework. So I said you can intuitively understand this. Let's think in terms of really concrete things. I want you to negate the following statements and think about what you mean when you're negating them. Let's say I have the statement, it is raining and I live in Seattle. And the statement, tomorrow is Thursday or Friday. So let's try to write a meaningful negation. Well, if someone said, it is raining and I live in Seattle, and you want to express the opposite of that, how would you do it? To negate it is raining and I live in Seattle, you would say it's not raining or I don't live in Seattle. So the negation of this is it is not raining or I don't live in Seattle. Right? You wouldn't say it is not raining and I don't live in Seattle. That's not the negation of it is raining and I live in Seattle, because for it is raining and I live in Seattle, for that statement to be false, it could just not be raining, right? If it's not raining and I do live in Seattle, that first and statement is still false, right? So if you put an and here, that's too strong for the negation, right? Which means that the negation of an and statement is an or statement where you've negated each of the individual pieces. Again, the second one, tomorrow is Thursday or Friday. How would you negate that? You'd say, well, tomorrow is not Friday and tomorrow is not Thursday, or tomorrow's not Thursday and tomorrow's not Friday. That's how you would negate tomorrow is Thursday or Friday. And so tomorrow is not Thursday and not Friday. Right? To negate this or statement, you want to say that both of the things, it's both not Thursday and it's not Friday. You wouldn't want to put or there because that would be too weak to negate the statement. So if you can understand these examples, then basically you understand why demorgans laws are true. To negate an and statement, it's not rain, it's raining and I live in Seattle. To negate that, you only need one of them to be false. Either it's not raining or I don't live in Seattle. On the other hand, in order to negate the or statement, in order to negate tomorrow is Thursday or Friday, you want to say tomorrow is not Thursday and tomorrow is not Friday. So in order to negate an or statement, you get an and statement, and that's the second of De Morgan's laws. Okay, so hopefully this makes some intuitive sense. These are exactly the kind of logical arithmetic, you could call it, that you want to be sort of automatic. Because right now you can imagine that you're in some future math class and you're asked to prove something like, you know, if it's so hard for me to come up with examples on the fly. If something happens, then something and something, right? If set of vectors is linearly independent, then the matrix formed by taking those vectors as its columns has a pivot in every column, and the linear transformation is a one-to-one linear transformation. Right? If P, then Q and R. Well, maybe you want to prove it using the contrapositive, right? So, rather than boxes, let's just say if P, then Q and R. If P, then Q and R. Very common sort of statement that you want to make, right? If something is true, then these two other things are both true. And then you want to prove by the contrapositive, that's if not Q and R, then not P. In order to do that, you need to understand what not Q and R is, right? So it's really if not Q or not R, then not P. And then maybe you'll break into cases. You'll say, okay, well, suppose not Q, then you'll prove not P. Suppose not R, then you prove not P. The point being, negating ands and ors is a thing that you'll want to do all the time. It should become second nature. Okay. So that's how you negate an and and an or. How do you negate a conditional? Let's call this negating the conditional. So how do we negate if P then Q? Okay, of course you can negate it by one answer that's correct, but maybe not that helpful, is you can just put a not in front of it. But I'd like to understand what this actually means. But we have some tools at our disposal, right? So we saw that if P then Q is logically equivalent to not P or Q. To say that the conditional is true means either the hypothesis is false or the conclusion is true. Which means that if we want to negate if P then Q, we can just negate the right-hand side, which is an or statement. So I can use demorgans laws. I guess the second one I wrote down. So the negation is logically equivalent to the negation of this, right? Which, by De Morgan's laws, if I want to negate an or statement, what I do is I negate each part and I put an and between them. Okay, but not P is the same thing as P. That's an easy proof. You just write down a truth table. So this is the same thing as P and not Q. Which again, should hopefully make some intuitive sense. Because this entire time we've been saying, when is the conditional false? The conditional is false exactly when P is true and Q is false. Which is exactly what this whole line is saying. This is saying that the conditional is false exactly when P is true and Q is false. The negation of the conditional is the same thing as P and not Q. Okay, so let's write a negation, a meaningful negation, to my favorite conditional. If it is raining, then I will bring my umbrella. Okay, and the negation to if it is raining, then I'll bring my umbrella is it is raining and I will not bring my umbrella. That's how that statement could be false. So if someone says, if it's raining today, then I'll bring my umbrella, and you wanted to contradict everything they were saying, you would say, it is raining today, and I will not bring my umbrella. Which is exactly what that line is saying. To negate the conditional, if P then Q, that statement is P and not Q. Okay. So one thing that we saw from this line, or this argument, is I'm using a bunch of stuff here in order to conclude this second line using De Morgan's law. I was writing down a bunch of logical equivalences and sort of explaining them along the way. But like, for example, we've never discussed that not P is the logical equivalent to P. And it's a thing that I wanted to use here, but technically I shouldn't have because we never used it. We never discussed that it was true. So what I'm going to do, and what your book does, is it just provides a theorem with a bunch of logical equivalences that we can use if we're trying to work with logical statements. So here's the theorem, and we should think about why these are true. And I will probably ask you to justify, maybe with a truth table or maybe with an argument, some of these things on your next homework. So let's let P, Q, and R be statements. Then I'll just write down a list of logical equivalences. Okay, so we already said that a statement is logically equivalent to its contrapositive. I include it here just so it's all in one place. So we also said that if P then Q is also logically equivalent to not P or Q, that's the thing that we used on the previous slide. We also said the negation of the conditional is the same thing as P and not Q. Right? Hopefully that one is understandable. A thing that we said earlier but didn't write down is the following: P if and only if Q is logical equivalent to if P then Q and if Q then P. Again, I'll ask you to prove some of these on your homework, but to be honest, the proof is quick enough that you could jot one down right now if you wanted to. The thing that we used in the previous thing is the negation of not P is logical equivalent to P. So as far as logical equivalences go, you can sort of cancel double knots. Okay, here's a useful one that we haven't discussed yet. So maybe it's a candidate for a homework exercise. If you take P or Q and R, what is this logically equivalent to? P or Q and R. That's the same thing as P. Sorry, I've written down not what I meant and not what's in your notes. So let me, P or Q and R. So this means that P is true or both Q and R are both true. And you can show that this is logically equivalent to P or Q and P or R. These will be true in exactly the same situations. Namely, if either both Q and R are true, then both sides will be true. Or if P is true, both sides will be true. Or if all three of them are true, then they're true. In every other circumstance, both sides will be false. Okay, so what this does is it tells you how or distributes over and in some way, right? This is like a distributivity law. This is like a distributivity law for or over and. Maybe I'll use the symbols. Okay, so we'd also want something in the, for how you would distribute and over or. So this is the same thing as P and Q or P and R. Right, because let's think about this again. The left-hand side, that's true. Well, that means that's true if and only if P has to be true and Q is true or R is true or both. Right, that's the left-hand side is exactly true when P is true and one or both of Q and R are true. In order for the right-hand side to be true, at least one of this one or this one needs to be true, which means that P definitely has to be true, and at least one of Q or R is true. So these two statements are true in the exact same situations, which you can of course justify with a truth table, but you can intuitively understand by thinking about when these two statements are true. So that's a useful one that tells you how to distribute and over or. Okay, here's another one. We sort of discussed something like this earlier. If P, then Q or R. Again, a common sort of statement in mathematics. You suppose P is true and you want to prove that, well, that means that Q is true or R is true. Okay, and this is logically equivalent to P and not Q implies R. Okay, and I claim that you've actually been using logic like this your entire life. You want to prove that if P is true, then that implies either Q is true or R is true. You say, okay, well, suppose that P is true and Q is not true, then that must mean that R is true. That line of reasoning is exactly what's presented in this logical equivalence. Let me say that again. Suppose you're trying to prove that, oh, suppose P is true. I'm going to prove that Q is true or R is true. One way to prove that is to say, well, suppose that P is true and Q is not true. Then I'm going to show that R must be true. And that's exactly what's captured here. If P then Q or R, or P implies Q or R, is the same thing as P and not Q implies R. And you can prove that again using a truth table. And then the last logical equivalence in this theorem is if P or Q, then R. P or Q implies R. And this, again, is the kind of logic that you have probably used your entire life without thinking about it in this way. this is logically equivalent to P implies R or Q implies R. Right? So I want to prove to you that if P is true or Q is true, then that implies that R is true. Well, I'll show you that P implies that R is true, or Q implies that R is true. Now that I'm thinking about this, do I have the right thing written down here? See, it's not that easy for me to think about this either. So you know what? It's a good example. Let's do this with a truth table. Let's make sure that I've written down the correct thing. This is too wide. I wonder how it's going to print when I print this. I probably don't need that last column. So one example for your notes where it's done out in complete detail. So here we have 3 statements, P, Q, and R. So I'll need 8 rows to this truth table. Again, the way that you write down every situation is you alternate with half the period as you go along. So true, true, false, false, true, true, false, false, and then true, false, true, false, true, false, true, false. P or Q, that's true as long as they're not both false, which only happens down here. P or Q implies R. That's only false if P or Q is true and R is false. That's only false here, here, and here. Otherwise, it's true. P implies R. That's only false if P is true and R is false. So that happens in the in the second case, in the fourth case. Otherwise, it's true. And Q implies R is false only if Q is true and R is false, which happens in the second case. In the 6th case, and that's it. And then the or here shows that I've made a mistake, right? This should be an and. Okay, so I should fix that in the notes. So now if I and these 2 columns together, you will see that I get that this column and this column are exactly the same. So if you want to prove P or Q implies R, you can prove that P implies R and Q implies R. Therefore, if you have either P or Q, R will be true. Right? So the reason that I knew that the statement that I had written was false was because when I thought about the logic, I realized that the logic was not what I meant. Okay, so this you can think of as, this is really breaking into cases. If you want to prove if P or Q is true, then R is true, you say, okay, well, if P is true, then R is true. If Q is true, then R is true. Therefore, if P or Q is true, then R is true. Okay, so these kinds of logical equivalences are things that we'll want to use frequently. Okay, well, that's, I think, roughly 50 minutes. So next lecture, we will talk about sets, which is section 2.3 in your textbook.